Hello calculus students, continuing with our video here, we solve part B. So if we look at part C, the problem becomes quite simpler. When will the population reach 90? Well, you set this equal to 90 and you solve, and you can solve this your favorite way, whatever that may be. Okay. So I'm going to say here, I'm going to solve by graphing. Okay, so after I solve, the graph of P of t looks like this. It starts out slow, grows very fast, and then kind of starts to level off. And the line y equals 90 intersects it at about 28.367. So that's going to be our answer. So I'm not going to go too much into this. This is more of an algebra problem. I'm going to really want to focus with you on part D and C here. So the answer to T here is after approximately 28.367 units of time. In fact, it doesn't really tell us what the time here is exactly. Okay. Alrighty, so part D, when will the population's rate of change start to decrease? Okay. So what's important here is that it's asking about the rate of change. When will the rate of change start to decrease? And the rate of change is dp dt. In other words, it's asking when will dp dt start to decrease? So if we think of dp dt, or p prime, when will that start to decrease? Okay, and you can see here that at some point, when p is very very small, the rate of change is increasing. In other words, you can see it on the graph here. At first, notice here that the population is always increasing, but earlier on it's increasing at an increasing rate, and then at some point it starts to level off, so it's increasing at a decreasing rate. Okay? So what we really want to know is, when does p prime start to decrease? Okay? And in order to solve that, we need to find the second derivative. Okay? So I'm going to solve this generically. dp over dt was equal to rp times 1 minus p over k. All right? If I want to take the derivative of this, then I get d squared p over dt squared, and this is the notation for the second derivative, which is equal to the derivative of the first, which is r, times the second, plus the derivative of the second, which is negative 1 over k, times the first, which is rp. Okay? And then I'm going to set this all equal to 0, and then solve for p. Okay? So set dp squared dt equal to 0 and solve for p. Okay? So again, just to back up, we want to know when will the first derivative change from increasing to decreasing, and in order to do that, what we're really doing is just finding the critical point of the first derivative, so we got to take the second derivative. So 0 is equal to r times 1 minus p over k minus 1 over k rp. I'm going to rearrange everything. rp over k, so that's just taking this term to the left side, is equal to, and then I'm just going to sort of distribute everything, r minus rp over k. Okay, so taking this, bring it to the left, taking this r and distributing it through here, and you can see that I have the exact same terms here. So if I add this to both sides, I get 2rp over k is equal to r. Right? And then I'm trying to solve for p. Okay? So I'm going to multiply both sides by k over 2r. So that's gone and that's gone. So this occurs generically when the population is equal to 1/2 of the carrying capacity. Okay? So to answer our specific question, we can say when the population is equal to k over 2, and in this case k was 100, so when p equals 100 over 2 or 50, the rate of change goes from increasing at an increasing rate, so goes from increasing at an increasing rate to increasing at a decreasing rate. Now notice here, this is not in terms of time. If you wanted to solve for time, you would have to set this equal to 100 over, you have to plug 50 into the function for p of t in order to solve. Okay? So 97 over 3e to the negative 0.2t. Okay? So if you wanted to solve for this, find the exact time, you have to solve this equation. In the interest of saving us some time here, I'm going to solve it by graphing and then give you the solution. Okay, so I graphed it, the line y equals 50, and I get that it occurs at time 17.38. Okay. So this occurs at t equals 17.38. Okay. So just go back to it, let it digest for a little bit, and make sure you understand exactly what we're doing here. Okay, because we're not really solving for when the population decreases. The population never decreases. It's always increasing, but its rate of increasing changes from increasing at an increasing rate to increasing at a decreasing rate. Okay? And now we have one little problem left to solve. When will the population reach 200? Well, the answer is never. And how can we determine that? So one thing that we can do is for part E, we can take the limit as t approaches infinity of p of t. Okay. Now, if you take E, or any base really, and you raise it to a gigantic number, what will happen is you'll get to a gigantic negative number. What will happen is that you will get 1 plus, okay, and all of this right here, if you raise all of this here to a very, very large number, large negative number, the whole thing here will approach 0. Okay? If you plug in a very large number here, this whole term will go down to 0. So that's all gone, and this comes down to 100. Okay? So the answer to that problem is never. It's never going to reach 200 because the maximum that it will ever reach is 100. In fact, if you look at the graph, it sort of confirms this idea. Starts out small, increasing, and then levels off. Okay. So now you can see why we call this number up here. Remember that this is k. We call this the carrying capacity because as time marches forward, the population can never go above this number. Okay. If it did, you would have a completely different scenario. So now I want to go back a little bit to a couple videos before, and I don't know if you remember, but we made it to this step here, right? And I wanted to stop right here, but had we stopped right here, it would have been pretty difficult to find. Like, it's difficult to determine the limit of p of t as t approaches infinity, because you would have infinity up here and infinity down here, and that's not something that we could reason through logically. Okay, but if we continued and since we continue and we solved it into this form, as t goes to infinity, it's really easy to see that this whole thing here, this entire term will reduce down to 0, and then the entire function will approach 100. Okay, so there you have it, a very whirlwind tour through the world of logistic equations, but I hope that you don't get too lost into the algebra of this. If you do, we can work through it some more. Ask your teacher for help. But most importantly, it's critical that you understand, the concept behind this, which is, again, that you start out with a basic differential equation with certain characteristics, and once you work through all the algebra, you get a very unique form of this. In fact, you get a generic form of this that looks like this. Remember, you get a very generic form where this is the carrying capacity, this is some constant, and R here is they call it the growth capacity, the growth parameter. And R here determines how fast that curve grows. Okay, but K determines the total population that it could grow to, and it all starts from that basic differential equation. Again, thank you for watching. As always, ask for help if you need it. Have a wonderful day.